Okay, our next speaker obtained his PhD at Steklov Mathematical Institute and remains affiliated to this day to the Steklov Mathematical Institute. In 2008, he also became affiliated to the University of Chicago. He has been distinguished in many ways. Let me just mention a few of them. He received the Nevalina Prize when he was just 27 years old. He was awarded the Gödel Prize as a member of the American Academy of Sciences, the Academia Europea, and corresponding member of the Russian Academy of Sciences. But what is more impressive is that he's well known for his many wonderful and powerful contributions to TCS, among them the notion of natural proofs, together with Stephen Rudish, and a result whose proof when I first read while in grad school in a complexity survey by Bopana and Sipser, I vividly recall thinking that it was the most beautiful proof I have ever read in my life up to that moment. And I'm referring to the super polynomial monotone circuit complexity lower bound for clique. More recently, and I believe much related to his talk today, he introduced the notion of flag algebras, thus significantly contributing to the development of the theory of limit objects and extremal combinatorics. So it's my great pleasure to introduce our next speaker, Alexander, known to most as Sasha Razborov. Thank you.
All right, thank you very much for the wonderful introduction. It is my great pleasure to talk at this conference. So I was very honored to accept the invitation. That said, it is the most unusual talk I have given in my life at a major conference, and probably it is the same for most of us. I envision the situation when my grandson will ask me, Daddy, how come that you had Latin 20 in 21? What happened? How was it possible? And you know what I will tell him, or sure. I will say, young friend, at that time we took conferences seriously and we did it on the centennial basis. So it refers to 20th century, Latin 20. Anyway, so we are still in all this together. So let me at least try to entertain you in these bleak times with something less exciting maybe. And it is really what I am going to talk today about. It is really several years of research, of our research with Leo, and I have something like 50 or maybe 55, 50, I guess, minutes. So I have to make some hard decisions. The first decision is that I really won't say a single word about why these things are important. If you are here, then I presume that you are convinced that studying huge objects in combinatorics using analytical and algebraic tools is a cool thing to do, that limit objects are important, that quasi-randomness is important. I don't want to tell you anything about the connection with other areas. Just let me say there are many of them, really many of them. So I will try to compensate it with examples and other stuff. So as long as the technical part is concerned, this disclaimer is very important. So like everything in this area, it stemmed from the theory of ordinary graphs, and we have absolutely nothing to say, nothing new to say about ordinary graphs. If it is the only kind of combinatorial objects you are interested in, then I suggest you don't waste your time on the rest of the talk. That's very important. Don't expect me that I will say anything new about graph-ons. And lastly, again, it is also a difficult decision, but in the first part, I will basically introduce some language, and I will have to skip essentially what is interesting, or everything, almost everything which is actually interesting in our paper. I want to concentrate on new things. So let me make one more disclaimer. As many of you know, if you study limits of graphs, even of graphs, then there are basically several various regimes, density regimes. So it is just the H density. So each one has its own name. So they are quite interesting names. So it is a dense regime when the constant density, sparse regime when you are basically talking about k-regular graphs for a fixed k, and this intermediate regime where people were able to start doing things only relatively recently. So this is my disclaimer. So in my talk today, I will be only interested in the dense regime where we have well-established theory, at least in the graph case. Right, so one important thing I forgot to say is that if you have any questions during the talk, please ask them. You can unmute them and ask by myself or my co-author, Leo. He's also here. He kindly agreed to monitor chat and answer questions there. He can say about this stuff as much as I can. Well, I mean, at least as much. Good, so any questions so far? Right, here is some literature. Basically, this is geometric theory of graph limits, which is called graphons. This is algebraic theory, and these are the two papers I will be talking today about. They are available from our website if you forget to write it down. So let's move on. So on the next slide, it is, if you are familiar with flag algebras, we work in the same degree of generality. I will remind formal definitions at my next slide, but for now, this is an example of structures that are covered by this theory. So all kinds of graphs, all kinds of hypergraphs, directed graphs. You can introduce axioms like you do when studying Turing densities. You can color everything you like, and blah, blah, blah. So there are many things that are covered. There are a few things that are either not covered or covered in a non-trivial way. But let me, for those who are not familiar with flag algebras, let me remind you the most basic definitions. So it is our setup. We are in first order logic, with the restriction that we don't have any function symbols, any constants, only predicate symbols, and all axioms are universal. I will sometimes use the word open for them. No quantifiers also. If you have quantifiers, then the whole thing breaks down immediately. And actually, the only reason to consider these restrictions is this one. So by that, we know that if we have a good notion of induced submodel, if I have a model in my theory and any set of vertices, then I can induce and get induced submodel. That's why we need all these restrictions. Right. So let me show a few more examples. So this one will be extremely important for the second part of the talk. So if you have two theories, T1 and T2, then we assume that their languages are disjoint. Otherwise, you rename your predicate symbols. And it is just you put all this together without any new axioms. It's simply the theory of you have several structures on the same ground set, and that's how you described it. And here you described it. And here are a few examples. You can look at arbitrary structures T, and you can color vertices in C colors where C is fixed. Sometimes you want to color them in an unbounded number of colors, say which depends on the size of the structure. Then you cannot say it in this way, but you still can look at the corresponding equivalence relation. And then you can still say in this language many things you may want to say. And this is also very important in finite model theory. That's basically two cases you distinguish. Ordered models or models where you have pre-installed linear order on the vertices. So that's another example, and we will see many of them in the second part of my talk. So let me show you a few more non-trivial examples. So simplicial complexes. A simplicial complex for us, it is simply a downward closed hypergraph, not regular, it's downward closed. So, and as long as the dimension d is fixed, then you can obviously express it in our language. Simply for every k, I believe it is k minus one dimensional phase. It is simply true if and only if it is k minus one dimensional case, and these are obvious axioms. So these axioms are present always in all our theories. We really don't want to mess around with the case of equality of some of our variables. It makes sense in the limit theory, of course, because you never see equalities in an infinite object. So it makes sense. It is always present. Here is how you say simplicial complex in our language. This is my favorite. So permutons. Permutons capture finite permutations, and if you look at finite permutations and what it is a function which looks like that, a bijective function from a set to itself, and there is no way you can say it in our language, it seems. Because if I induce on 134, then I get nonsense. But not so fast. Here is another way of representing permutations, and that's how it actually appears in many textbooks in algebra. So it is simply what we see here. It is a linear order, two linear orders on this set 1, 2, 3, 4, 5. The first one is natural, and the second one is given by my function f. Then you can perfectly say what is a permuton in this language. It is simply you have a model of this theory, which is two linear orders on the same Brown set. Well, that's a permutation, and so when we come to the limits, that's another way, after this great paper, it's another way to get limits of permutations, equivalent. All right. Right, I had to do something special for this conference, so Latin squares. And the question mark means that Leo and I, we did not check it as properly, and as we checked other cases, it may or may not work. So what is a Latin square? Latin square is a square like that. So again, we don't like this description. We look at the source, at the universal source of human knowledge, which is Wikipedia, and we see this definition. So, and actually, this is like Kabbalists thought about Latin squares for a long time, right? These are three independent attributes: row, column, and entry. So this is Latin square. It is a set of three values to three independent attributes with this condition, and now it is perfectly expressible in our language. Yes. So you look at three linear orders on the same set, and you only have to introduce this restriction, which is very serious restriction, but still it's manageable, that if I remove any linear order out of that, then I will get a permuton, and we must require that all these permutons are quasi-random. That's how you get Latin squares. Right, here are words. So how do we encode this great word abracadabra in our language? Here, actually, I don't even want to cross it out because you have to do very little work. You consider letters in your alphabet as colors. You look at the natural ordering of your word. And you simply see that, for example, the theory of words in this language, which is linear order plus 5 coloring, it captures exactly the limit theory of words in 5-letter alphabet. Right, good. Enough with examples. Any questions? Right, good. So this is the most fundamental, as it turns out, it is the most fundamental notion in the whole theory, which appears in many different contexts. So here we have two models in my theory, M and N, and I am looking at the density that will be denoted like that. It is simply the densities that if I pick m vertices in my whole universe of V of n, then I will see an induced submodel. And P stands for probability. It denotes the probability that I will see there something which is isomorphic to M, up to isomorphism. So if you are familiar with graph limits, then for graphs, it makes perfect sense to consider similar notion based on graph homomorphisms. But in our situation, we really want to cover situations when there is no such thing as an H. We've seen several such situations, no such thing as H density. We really cannot rely on it. That's how we have to operate. But if you are interested in graphs, then, well, it's, for example, in Lovász book and in many other places as well. These two things, they are equivalent. You don't lose, you don't gain anything. Another fundamental notion after we know what does it mean sampling is convergence. And convergence is defined in a very primitive way. We say that a sequence, convergent sequence of combinatorial structures, a sequence is convergent if these densities, they converge to something for an arbitrary template model. So let me remark that there is no restriction here on rate, on uniformity, etc. And after I spoke about these things in some algebraic audiences, that's the disclaimer I have to make, because they immediately, when they see this thing, they immediately think about something like direct limits. There is any way to connect models in my sequence? No, that's not the case. They are the only thing they are connected to be convergent is by this formula. So one slide, flag algebras in one slide. So what we can do with this set of limit densities, we can form a commutative associative algebra A of t and arrange them in the form of algebra homomorphism to the reals with certain positivity conditions. So, and as again, most of you know, it turns out that this equivalence to convergent sequences to other things we are going to discuss soon. So, and Lovász invented this term, well, not actually invented, he referred to someone, this term cryptomorphic. No one, including myself, actually understands what it means. There is no such thing as a rigorous definition of cryptomorphic, but I love this word, I'm going to use it nonetheless, or maybe because of that. So we will see it later. So, and just one slide, what we don't do about flag algebras today. So what we don't do, we, first of all, even in this restricted language, when you only have the sequence phi and nothing else, you can still define many things. Well, that most of you probably know. If you do concrete computations using sum of squares, then you can actually prove interesting stuff in extremal combinatorics. And there are many examples by this point. And so this is very interesting recent research. I really evaluate a lot. It shows that these special finite SOS are actually not as different from those SOS most people are think about in combinatorial optimization. Right. Anyway, skipped means skipped. So geometric theory, let us start building it with the notion of a graphon. So what is a graphon? A graphon is simply what you might think about it. It is symmetric measurable function, where say omega is 0 to 1, and W stands for rate. So xy stands, so W of xy is sort of the probability to see the weight. We think that xy are connected with the h, with the probability wx of y. And very well kept secret in this theory of graphons is that there is absolutely no such thing as random sampling from omega. I mean, if you want to form even a random subset of omega, then you absolutely cannot do it. there are good measure theoretic reasons to prevent this object from existing, like random subset of 0, 1. But as computer scientists, we of course, we don't care about these things. We still argue about non-existing objects. We do it all the time. So, and with our intuition, it is clear how to define the densities of graphs in a graphon. This is the simplest case of case 3. You just sample at random 3 points, and you write down this kernel, which tells you what you see in this sample, and you define the corresponding densities. So for every graph, for every graphon, you associate phi w, and the fundamental theorem, which is easy in one direction and very difficult in another, it says that it is just the same as convergent sequences, and as I said, it is just the same as Flog algebra homomorphisms in this algebra corresponding to graphs. Good. So far, so good. So now let's, as I said, we don't have anything new to say about graphons. We have to move on. And for those of you who have not seen hypergraphons before, it is really something, right, you choose the word, I don't want to impose. So what would be the natural attempt to define hypergraphons? Three graphons, for example. Natural way would be something like that. You just replace 2 by 3. Does it work? As many of you know here, it does not work. If you look at quasi-random or just random graph G of in the Erdős-Rényi model, and you look at the set of all its triangles, they form 3 hypergraphon, you really cannot express it this way. The only thing you can do is just mumble that the H density is 1/8, obviously, so you may try to describe it in this way and you will fail. It's very easy to construct an exercise, how exactly you fail. So we need something which is very bizarre. After many years of working with this, I still don't understand how it works and why do we need them, but we need higher order coordinates. So, and to introduce them, we really want to take another view at graphons. So a graphon is just a function from this set to that set, and every function, it has a graph. And the graph is described here in this peculiar annotation. We introduce one more coordinate, and we describe a graphon with this graph. So, and in the opposite direction, it's a subset now in this set. In the opposite direction, if I have a measurable subset here, then I can define a graphon in Lovász sense by this formula. I'm sorry, my screen. I hope it's still here because it is blocked on my screen. So it is simply as a measure, you look at slices corresponding to averages here by Fubini's theorem, almost all of them are measurable, and you define this. So these are actually 2 equivalent descriptions. And let me immediately move on to Theons. So you give these very natural definitions. So when k is equal to 2, then you recover the previous slide, but in general, you look at coordinates. Let me immediately show you how it looks in the case k equal to 3. So you define hypergraphon is just a symmetric peon. Peons in general are arbitrary subsets. You just introduce these crazy new variables. What they correspond to, don't ask me. You need them to run a theory, anything like a theory. I don't have any intuition about that. That's what we need. So, and then, as we will see, the theory will work out quite nicely. So let us first, so it is all parallel with how you define models and model theory in first order logic, only now we shift the focus from looking at first order formulas to densities. So again, I remind my setup. Ki is the number of arguments of pi. So the first step is very trivial. If I want to describe a model in our sense of the structure, then I do it before I have any axioms. Before I have axioms, I just describe them, those models in a very natural way. For every predicate, I describe its interpretation. And T-ons, you can, after you do that, you can, in very natural way, to define the set actually of those points in your theon. It will be a subset of En, and is a number of variables for every open formula. You can define its truth set just in the same way, almost in the same way as you do in model theory from mathematical logic. So it is the most painful thing is to define it when you have atomic formula for individual predicate, but it basically, I don't expect you to read it, but it basically says that all definitions are very natural and you can move things around. So you can do it in a natural way, and then you say this magic sentence that it commutes with logical connectives. If you put disjunction or conjunction, then it will become union and intersection, but otherwise there is nothing interesting here. And now comes my main definition of theon. As you might expect, it is a theon of a series anything that satisfies its axioms. But here there are two different possibilities, and both of them make sense. First of all, for some technical reasons, we have to exclude the diagonal. Let me not say too much about it, but even without the diagonal, you can either say that your axioms are satisfied almost everywhere, or they are satisfied always. And it brings about, let me see what's on my next slide. Yes, we will discuss it. Let me now finish my definitions, and then you can define what we actually want to define. If I have a model M, then I can define its density in a theon. So it is this formula. You can do it directly, or you can reuse the theory. Namely, you can describe this fact as a first-order formula, quantifier free formula, and reuse my previous definition. Whatever you do, you will get, of course, the same thing as for graphons and for all other situations considered in literature, that every convergent sequence converges to a theon. So far, it's a straightforward generalization of Lovász theory. Well, we have seen many of them to arbitrary theons. This is the main cryptomorphism, whatever it means. So now what we also have, again, mostly after Lovász's book, we have a few other descriptions based on exchangeable local arrays, several versions of it, all of them work here. And we have existence of theons is actually here. And also we have uniqueness of theons under a special set of measure-preserving transformations, which are a bit messy to describe. I will not do it here. Questions? Very good. And one more thing that I want to say here before we move on is this very important notion. If you look at the combinatorial literature, then it's everywhere. Interpretations, how you move around. I will show a concrete example on the next slide, but how you move around information from one theory to another. So it is simply, it's very easy to give a formal definition, which I don't do here, of course. But the idea is that if I have any model on the right, then I can convert it to the model on the left in a natural way. For example, every tournament is a digraph, directed graph. Every linear order is also a partial order. Every triangle free graph is a graph. So that's one way to do it. Another way is you may erase, and it will be very important in the second part of my talk, you can erase structure. So for example, if I have directed graph, then I can view it as a graph simply by erasing the orientation on the edges. So, and let me show you one non-trivial example. These two series and these two kinds of combinatorial objects, of course, are very different. You know, the graphs and tournaments are very different. If I add linear order to both of them, they will become isomorphic. They will become the same, which is, I forgot the term, feedback arc or whatever it is, interpretation. Anyway, if you have a tournament and linear order on it, then you can simply declare those pairs that go backward as an H, those that go forward as non-H, and in this way, it is isomorphism. You will get a graph and vice versa. So for all purposes of this, for all our purposes, these series are the same. They are isomorphic. And it was implicitly used in this great paper by Chang, Graham, and Wilson, where they studied random tournaments, quasi-random tournaments, and that's the way how they were able to recycle the stuff from the graph theory paper, and it is really everywhere. So, and, right, I'm not sure that it is the right thing to say in this particular audience, but it's all natural. So it's really a nice category, and whatever you do, we will see a few examples. It behaves like a functor, which means that you can, if you have an open interpretation, it's the right way because you can move everything around, including, for example, Theons. If I have a Theon, then I can apply to it my open interpretation. Anyway, so I'm half time through, so it is the time to move on to the second part. So that's what I have skipped about Theons, about the general theory of limit objects. Essentially, I skipped everything interesting because what we have seen so far is just a language. So let me just mention a few things that I have skipped. The first one is that it's a very natural question. If I give you a big Theon, all axioms are satisfied almost everywhere, then can you somehow fix it so that they will be satisfied everywhere, except for the diagonal? Turns out to be a very difficult question, even for linear orders, by the way. We have general theorem how to do it with axiom of choice, and we don't know how to do it otherwise. There are very simple situations where it is open. And also, once you can express things in our language, then existence and uniqueness of limit objects becomes straightforward. You absolutely cannot do more sophisticated things. It depends on the context, but at least existence and uniqueness you always have. And this is some list of objects to which you can apply this theory and get existence and uniqueness for free. I mean, for free after we did all the work, and if you refer to it and appreciate what we did, then I will also appreciate it. All right. Message to take home. And to the second part of the talk. So the first part was mostly about the language I'm going to use. These are my reminders. So T is universal. This is our setup, the same as in Flock algebras, universal first order theory in some language. Convergence sequences of models defined just in the same way as you do it for graphs, density convergence. And you have two cryptomorphisms. You can describe them as these things in Flock algebras and as Theons, alternately. So if I have phi, which will be my preferred way, just because it's more concise, then you can represent it as a Theon in many ways, but there is at least one representation, and all of them are unique up to a certain group of measure preserving transformations that I don't define in this talk. And lastly, there is this notion of moving information around different theories, or maybe even the same theory, and it behaves extremely nicely with respect to everything. It's like the method of restrictions in circuit complexity. If you restrict everything, be it your circuits or propositional proof, whatever, by a restriction, you expect that it will behave well. I claim that it has the same importance here. Right, good. Again, it's very good time to ask questions. Right, then I am coming to our second part of my talk, which is what I call natural quasi-randomness. And what does it mean natural? It's not like natural proofs that Marcos mentioned. Well, maybe you can make a connection in a sense, but right, whatever. So it has several meanings in our paper. This is the practical criterion. You really want something that works in the same degree of generality, that covers all those situations, at least in a sense. And a practical consequence is that, of course, you cannot base it now on concrete densities because they vary from one situation to another. It's always different. So the question is whether you can say at least something intelligent here, and I think you can. So I cannot cite here all previous work on quasi-randomness. It's done in our paper. We try to locate most of it. What was really inspiring to us is the work on hypergraphs, some of which is here. It is because it essentially introduced this relativity concept, if you wish, in the world of quasi-randomness, that quasi-randomness it is a taxonomy. It's not like an object is quasi-random, completely quasi-random, or not completely quasi-random. There are several hierarchies, and it makes sense to study them. And that's what we are trying to do in this research. All right. So there is one paper in the whole area that I would compare with the treasure chest, and I hope you can guess what it is. So if you want to say anything new in quasi-randomness, then what you do, you look into this paper, and most likely you find it there, well, maybe in an implicit form. And so that's what we did. So here is one disclaimer. We did not attempt to state our theory in the language of convergence sequences that most people do. It will be inadequate, it will be confusing, it will not be instructive, and at least the only thing I can say as an apology is that we were not the first. There were at least several papers that also go in consistently limit language, and that's what we also do. We study Theons or phi and try to classify them, not convergent sequences that were used for motivation. Right, so our first notion is the most natural one, and it is also the most mysterious one. Here, I hope you can see it. I have reminded what I said about graphons. So, well, obviously it is not in our treasure box in this particular form. Graphons appeared later, and as we all know, graphons were inspired by this paper. But still, if you read it well enough, then You can see it there. So what is quasi-random graphon in our theory? It's a constant function. And I immediately want to represent this constant function in the geometric form of a Theon. So it is the representation. And what invariant thing you see here, you see that it does not depend on first order coordinates. It depends only on the second order coordinate. So, which makes it very natural, as we will see later, it is extremely natural definition to define, to say that a Theon is k-independent if and only if it has this property that it depends only on higher order coordinates. It does not depend on coordinates up to order k. So then we define our first class of quasi-random objects. It is the class of all objects that have at least one k-independent representation. And it is here, it is shown here in red for a very good reason, because you can have twisted representations. For example, if you want to represent a quasi-random graphon, you can do it in this crazy way. And it will still be a representation, because once you fix x1 and x2, then you will get still a set of density p. It will be different for different choices, but it will have the same densities. So essentially, it is very deep and non-trivial question if I give you a Theon, whether you can rectify it using the class of measure-preserving transformations I mentioned before. So, and it's very non-trivial question, and really some of the forthcoming parts of my talk, it is really about how you can approach this question. So the next property that we have taken from the box is this one. So a graph is quasi-random if and only if it has this property. For our purposes, of course, it is not good to say right H density. In general, we don't have any such thing as H density, but we can slightly tweak it. We can say that what we require is that if we induce my graph by half of all vertices, that it will remain the same, similar to the original, which is inducibility property. This is once more the disclaimer I have made. So how do you put it into our language? You put it in our language in a very simple way. Namely, we use this notion of couplings. So what does it really mean if you want to take half of all vertices in my graph? You want to couple your graphon phi with simply coloring in two colors and see what will happen. And it is, of course, a general definition. If I have two Theons, phi1 and phi2, then I consider all their possible couplings in this united theory, such that if I restrict it to T1 and T2, that is erase unnecessary information, then I will get phi1 and phi2. And that's the main object on which the rest of the talk is based. So unique inducibility for k equal to 1. Then now we simply say that for any coupling of my phi, now phi is not only a graph but an arbitrary Theon, and random and coloring of my universe into colors, where p is the probability of the first color, that after I restrict C, and you can easily define it to the first color, then you will get the same Theon phi. So, and the way to define, to generalize it to arbitrary k is simply by observing that the theory of two colorings is just the same as the theory of this object, very sophisticated object, which is one hypergraph. One hypergraph is just a set. to specify a coloring into sets, into colors, you only have to specify its first color. The set of vertices colored in the first color, and now it is perfectly generalizable to arbitrary series T. And you say that phi is in use in this class. Now we don't have a restriction, but still we can say that the values of, let me remind you that Xi is simply a bunch of values. We say that those values, where M is such that it is a clique in K hypergraph, it was just a set of vertices of the first color, now it is a clique, it is going to be the same. So it's our second class. And so the third class is based on the notion of independent coupling, which is again very, very simple, very similar. So, and you can do it now in all worlds, and it will be very simple. So algebraically, you define this thing. Again, E1, I1, and I2 are structure erasing interpretations. So this is the model of the theory T1. This is the model of the theory T2. You can define it with this formula and check that all axioms of log algebras are satisfied. You can define the product of two Theons, which is very natural, or naively you just permute the vertices of two different structures at random and then couple them, align them. So as a typical example, quasi-random permuton is just the independent coupling of two linear orders. And now it brings me to my third and the last class, which is unique coupleability. So I clearly realize that at this point I'm going to be running out of time. The question is only was by how much. So I thought that at this point I should insert some non-trivial theorems in my talk. So, and this is the first actually non-trivial theorem, is that if you have any object phi, then and you take two numbers p and q between 0 and 1, you couple it with a random coloring in it will be uniquely couplable with colorings of density p, if and only if it will be uniquely couplable with colorings of density q. That's a non-trivial theorem, well, 5 or something like that pages of proof. So, and it gives us a good definition of U couple of 1. Again, I start with the case k equal to 1. We simply say that phi is uniquely couplable if and only if it has this property, which is natural. So basically, if you color your edges, your vertices of your model, whatever it is, in two colors, then what you see after that depends only on the density of your colors, but not on the way you color. So these are some examples. As we have seen, couplings of linear order with psi p is just the same as binary strings, as long as you as you require density p. As we know from the previous work, there are strings that are not quasi-random. Therefore, it is obvious that linear order is uniquely inducible, right? If you induce it to any subset, then you will see the linear order. There is nothing else you will see here, but it's not uniquely couplable. Follows from this work. So if you go to quasi-random permuton, look at your independent coupling of two linear orders, and it becomes even worse. It will not be even inducible. It requires an argument, but it's not very difficult. So, and unique couplability, it's actually, it is clear how you want to define it. The only thing you have to specify is what is the set of tests. You say that phi is in U couple of k, if and only if it is uniquely couplable with some set of test objects like we have in k equal to 1. And again, it is very important. Here is the dual notion. So we look at Theons that have rank at most k, which means that now they depend only on low order coordinates, like k hypergraphs. And again, non-trivial theorem is that now the situation is just the opposite to this one. Namely, this notion depends only on phi. If you represent your phi with two different Theons, you will get the same rank, it will not change. And so that's our third definition. All right, any questions? Then a few results, and then we will do open questions. Well, first of all, as I said, I really consider it as an ultimate test for being natural. All these things, all our classes, all notions are closed under interpretations. If you have a quasi-random structure from my class, from one of our classes, and you define anything from that structure, it will remain quasi-random. That's the test we have to pass, and we pass. So now these classes are closed under independent couplings. And as we have already seen, it is not true for the class of unique inducible objects, even for k equal to 1. They are not closed. Right. The next class of results is better illustrated with this page from our paper. So we have these hierarchies that looks like that for an arbitrary t. So all vertical arrows are easy to prove. The relations between unique coupleability and unique inducibility follows immediately from definitions. This one is not easy, and it does require an effort to prove it. But once you do it, you are well rewarded. Let me start with the remark, because now you have very practical way to show that something that is Theon cannot be rectified and reduced to k-independent form. You just show that it is not uniquely couplable with any test of yours. You take an arbitrary object of rank k, compute a couple of densities, and you show that your Theon is not independent of k. This is how a typical result looks, how a typical separation result looks. All of them work, even for hypergraphs, for hypergraphs. It's a typical separation result. What else? This is our most difficult theorem, most difficult to prove. So is there any universal set of tests? Right, you couple of k means that you can couple with an arbitrary, it is uniquely couplable with an arbitrary object of rank at most k. Turns out that you have to consider only this class of objects. You look at all, yes, you look at quasi-random hypergraphs, so it is the dimension in all smaller dimensions. Take the independent couplings, and you see that it is a universal set of tests. I think it's something like 20 pages of proof altogether, and you have to introduce some theory to do it. So very briefly, what else can we do? This one is very interesting, I think. It's one of the characterization of unique couplability in terms of inducibility. Turns out that something is uniquely couplable if and only if it is its independent coupling with linear order is uniquely inducible. That's something very interesting. So we can relate our hierarchies to those that were known for hypergraphs, and upshot there are a few non-trivial relations, but they are mostly incomparable. They go in different ways. So you can describe unique couplability in terms of weakened form of independence. I don't have time to tell you what it is. And you can characterize full independence. Also, this is the case where usually objects tends to be fully independent when it is one level below the maximal arity of predicates. For example, for hypergraphs, it will be L-1, where L is arity of your hypergraph. Usually, things tends to be fully quasi-random in this regime, again, as it was in the previous work. And in our case, you also can at least describe them in a constructive way. We can also do that. And the absolutely last topic that I will show you, and then we will move to open questions, is that quite ironically, it looks like even if you try your best and work very hard to avoid densities, turns out the densities step in anyway. You cannot really avoid densities in this business. It's ironic, but I feel we still have to report on our findings anyway. So it is a slightly technical definition. Namely, this is all these are just elements of log algebra. It is normalized in such a way that it measures the density of ordered models, not only that you are isomorphic, but you really have an isomorphism. So more general situation, if you have several subsets V1, VR on your set, then you can form this element that measures the probability of this event. I sample endpoints in my object and look at the probability that I will see M1, M2, and MR in their appropriate places. And you can do just the same thing as here, but you now return to isomorphisms and look at the probability to see something up to isomorphism. So if you know of log algebras, if R is equal to 2, and V1 and V2 are disjoint, then this is how you define multiplication. So a few definitions. Let me remind you what is an incomplete.
Sasha, I think we're on time, so.
Okay, good.
Okay.
So can I show open questions?
No, yes, just.
Oh, it's my
Let's
last
round
slide.
up.
It's my last slide before.
Oh, okay, good. Okay.
Deal. All right. So it's an incomplete K design. If the intersection of every two sets here is of size at most K, I will have one more slide, but it's very short. So, and we introduce these two classes, locality and symmetric locality, defined completely in terms of densities. So basically, it says that these events, ordered and unordered, are independent, complete density condition, and I hope you can guess what is coming now. These two purely syntactical definitions, they describe things that we defined in a very different way. And again, it is how things happened in the general theory. Right, good. So if you, as many of you know, you don't get famous by proving great theorems, you get famous by asking great questions that other people may solve. So let me just spend 2 minutes on doing that. Well, it's all recorded and papers are available. But the first question is very interesting because our class independence of K, it has very straightforward definition and we cannot analyze it. So is it closed in the density topology? Or more or less equivalently, can you describe it with density conditions? We don't know the answer, we don't have a guess. The second question we actually encountered in our research is, and we had to, in one of our proofs, and we had to turn around it. Right, it is here. Phi is uniquely coupled with a couple of objects. It might be natural to assume that it is also uniquely couplable with the independent coupling, but we were not able to do it, and we had to find a hot proof when we need it. It's also very interesting. So is there a Galois correspondence between unique coupleability and rank? So here is what it says. Basically, don't want to comment on it. And is it is the only separation that we were not able to prove, and due to certain circumstances, we don't even make any conjecture on this point whether it's true or not. But can you prove that unique coupleability implies independence at least in dimension 1 or k minus 1? And if you, that's Marcos, that's the last slide. So why do we believe that the quasi-random permuton is actually quasi-random? It's not even uniquely inducible. It is our weakest property. So it is open-ended, but it makes sense. Quasi-permuton will be in this, quasi-random permuton will be in this class. We close inducible objects under independent couplings and open interpretations. Can you say anything intelligent about this? Maybe it will explain why quasi-random permuton is actually quasi-random. And the last question is that we concentrated on the dichotomy, either something is has only objects, has only coordinates of size at most k or more than k, but it makes sense even for 3 hypergraphs to consider more general situations. So can you generalize this theory to the case when you look at an arbitrary set of dimensions like 1, 1, and 3, and so, and how much of this you can generalize? It's also open-ended. And now comes absolutely the last slide.
Thank you. So I invite everyone to open their microphones and let's thank the speaker for this impressive talk. So. And yeah, in the benefit of time, if there's some very short questions, we can take them. And yeah, so I had one, and we'll wrap it up. Also, Guillermo told me he wants to say a couple of words after we finish. So you stressed the fact that you didn't impose any restrictions on the rate of convergence at some point. This was early in your talk. Imposing conditions on the rate of convergence what does it change? What makes
No one knows, I guess.
Oh, okay.
I guess the honest answer is no one knows, even for graphs, and that's one of the great questions to study.
I see. So no idea what could change neither? Okay.
So it's basically it's sort of question whether simultaneous regularity lemma is really necessary here or something like that. It's an excellent question, and I think it's an excellent topic to study. I am not aware, maybe Leonardo knows, but I'm not aware of anything made in this direction.
Any other short question? Otherwise, let's thank again. And